Okay, so just to review, right? Oh, no, I have to type correctly. So we want net force equal to 0, net torque equal to 0, and as we talked about, this does not mean things aren't moving. This means that the acceleration is 0, right? Since F equals ma, and this means that the angular acceleration is 0, since tau equals I alpha, right? I mean, we've got net equals ma is where the a equals 0 comes from. We've got tau equals I alpha, right? So from these fundamental laws from Newton, if we're talking about statics, acceleration is 0, angular acceleration is 0, but the car can be moving at constant velocity, or the basketball can be spinning at constant velocity, or constant angular velocity, right? So it doesn't mean most of the problems we'll solve will be things not moving, because that's actually where statics is used most of the time. We really like for our buildings to not move.
So a frame that is moving, that's more like the universe, right? When you start looking at other things in rotational constant velocity, that's when you can start applying that.
That's right.
Yeah, that's cool.
That's right. And we do this all the time, right? We move into a frame all the time. Why? We're doing it right now in this room, where we're saying nothing is moving. But how fast are we moving? Right?
Yeah.
That depends on your frame of reference. Because if we go to, say, the sun and look at how fast we're moving, wow, the earth is spinning, and because of that, we're moving pretty fast already, right? I mean, we're moving at, let's say where we are, we've got 6,000 kilometers, so 6,000 meters, divided by 24, divided by 60, divided by 60. We're moving at 69 meters per second.
Does that speed differ the closer you are to the equator?
Yeah,
It does.
actually, I'm off. It's not, yeah, that's right. That's right. 1, 2, 3, 1, 2. Yep. Right, 69 meters per second, right now.
Crazy.
I'm just sitting here. Right? And then we add in, we're in 154 million kilometers. So add a few more zeros for meters. From the sun, divided by 365, divided by 24, divided by 60, divided by 60. Our motion due to the Earth going around the sun is almost 5,000 kilometers per second. Right? We're booking. So this whole thing about, okay, frame of reference, within a frame of reference, right? You can always find a frame of reference where things are sitting still. We have one right here in this room. All right. Now, if our frame, which is the Earth, were moving back and forth, we'd notice. If it were accelerating, we'd notice, right? Because all the chairs would be drifting towards one wall or towards a ceiling, right? So our frame of reference is not accelerating in that way. All right. So the other things that are in this chapter, all right? We have F over A is E onto. All right. What does this mean? What's that? Stress. Force per unit area is stress, right? So the modulus for stress, which we call Young's modulus, times delta L over L, right? Straightforward, pretty simple. Um, what it means is when I have a block and I apply a force to the surface at the top, right, it's going to get a little shorter. All right, and I think we worked a problem like this. It gets just a little shorter. Um, the next piece after stress is strain. All right, and strain is very similar to stress. All right, except now we're talking about movement in different directions. So the area that we're talking about is the same, but the force is now perpendicular to that, and what we're talking about is bending an object, right? Shear. I'm talking about the shear of this and moving it that way, and this G is the shear modulus. And the last one looks exactly the same, except that we now call force per unit area pressure, hydraulic compression, right? Bulk modulus times delta V over V. And the bulk and again, these are just within certain limits, these are all linear, right? So if the volume change isn't too enormous, this linear equation holds up. If the stress isn't too much, the linear equation holds up. If the strain isn't too much, the linear equation holds up. This is really an approximation for small changes, right? If you're going to take a piece of steel and compress it so much that its length changes by 50%, you're well beyond where these equations are going to apply. Right? You have to think of it in terms of molecular level. There's not that much room to move things around. You'd have to actually be deforming the object to change it that much, right? So these apply for small changes in volume, small changes in position, small changes in length, right? For some materials, compression and stretching are different constants, so you have to pay attention to that in the book, in the table there. One that you're all very familiar with in particular, not in terms of how it responds, but bone does not compress and stretch in the same way. Again, think of it at the molecular level. If the molecules are almost as close as they can possibly get to begin with, you can't compress it much. But stretching is a different matter altogether. You're asking for more room, not less. And there's certainly a lower limit to how much closer everything can get. But in a sense, until you break the bonds between molecules, there's not a limit to how much farther apart they can get. All right, so that's why those two are asymmetric for a lot of materials. Then you get to really interesting materials like degenerate stars, where all the electrons are in their own unique quantum state, and you can't compress it because there's not a quantum state for them to go down to. Right. So, all right. The torque problems, the statics problems are all about being careful, remembering that these are vector equations, right? Being careful about which way the torque goes, whether it's positive or negative, right-handed or left-handed, right-handed torque, positive, left-handed torque, negative. I'll post, I think I've got a good number of problems already posted, but I'll post probably some more. Exams will get graded here shortly.
Did you say the last equation was for hydraulic pressure?
Yeah.
Okay.
So it's a volume thing. And where this really comes into play is I don't think our book has the numbers in the table for us to do it. I may pull that out. When you freeze something, water is its most dense at 4 degrees C. It freezes at 0 degrees C. So water actually has more volume at 0 degrees C than it does at 4 degrees C. And as it freezes at 0 degrees C, its volume goes up. The amount of pressure it takes to keep water at constant volume and freeze it is enormous. Just enormous. Which is why there are a lot of things in medicine where if we want to store blood cells by freezing them, we have to dehydrate them first. Because if we don't dehydrate them, the water is going to expand and destroy all the cells when we freeze it. All right. So there's been a lot of work in medicine in particular in how do we dehydrate this so we can freeze it. And then at the other end, we have to reconstitute it with water, right? The fact that water expands so much as it freezes is why roads in the north break up during the winter, and they're always repairing roads. Because you get a little crack, water seeps in, it freezes, and it expands and breaks up the road more. So if you live someplace where you have freezing water all the time, roads do not last. And then there have been places that have used hydraulic expansion, different kind. Egyptians used to use hydraulic expansion when carving off large blocks of stone. So they'd get a little crack, they'd put a piece of dry wood into the crack, and then they'd pour water on it. And the wood would soak up water, and the cells would expand and crack off a block of stone. All right. So hydraulic expansion can be something that's really useful when you put it in the right area, and it's a really big pain when it's in the wrong one.
So this doesn't pertain to fluids. This pertains to just all kinds of hydraulic pressure.
All solids, fluids, right? Pretty much everything but a gas. Right. I mean, yes, it does pertain to a gas, but gases are, well, squishy.
Different. So take a fluid. Any fluid has a different. Like if you were to compress it to a state, I guess the pressure that it would give off would be different per fluid. Is that right? Some fluids give off very high pressure.
It,
When they compress.
the details depend on the fluid. Yep. Any other questions? The big takeaway from this is statics, which is that right there, which is, a whole course. Right? That's a whole course. All right. I will see you on Monday.